Welcome to my National Archaeology Week talk. My name is Professor Andy Herries and I'm an archaeologist in the Department of Archaeology and History at La Trobe University. And today I'm going to speak to you about when did it happen, dating our ancestors, because some of the things that I'm interested in is the origins of us. Where did we come from? But also, how do we work out the age of those fossils and the archaeology in the archaeological record? So who am I? Well, I'm a professor of archaeology. I'm a paleoanthropologist. Basically, I'm interested in human evolution. I'm a geoarchaeologist, understanding the archaeological context of artifacts and of skulls. In other words, looking at the geology and understanding how did that material get there. And then I'm a geochronologist. I work out how old things are. I'm the head of the Australian Archaeomagnetism Laboratory that you can see there in the top. So this uses magnetism as a way of dating the past, but also looking at things like past climate change. I also run 2 excavations and field schools in South Africa. The Drimolen Field School, which is a site that's about 2 million years old, which I'll talk about in the talk, and then Amunzi Springs, which is about 500,000 to about 100,000 years ago. And that one looks at the origins, the beginnings of when we became our species, Homo sapiens. If you want to follow me after this talk, you can find me on Twitter, OzArchaeomagLab. I post lots of pictures about lots of really nice places all over the world. So the Australian Archaeomagnetism Laboratory that I run, so this does a whole range of things. We do work out how old things are using magnetism. We use portable X-ray diffraction and X-ray fluorescence for looking at geochemistry, thin sections, geoarchaeological analysis for understanding how sites formed, geophysics for finding out what sites are buried under the ground. So we do a whole host of different things. We've owed that for the academic environment, but also for the commercial sector. So when we talk about dating our ancestors, when we think about archaeology or human evolution, when are we looking at in Earth's history? Well, the Earth is very old. As far as we know at the moment, 4.6 billion years old. And we as humans, even our sort of distant ancestors, have come onto that geological scene pretty late on. Our understanding of when the first fossils that represents humans occur is somewhere in what's called the late Miocene, around 7 to 5 million years ago. These are the first what we call hominins. These are fossils that are on the human evolutionary line, but they're very unlike us. They're still apes essentially, but they have this one defining characteristic. They stand upright like us. They don't have a big brain. They're not using tools yet. They're simply standing upright like us. And that's how we determine the beginning of what it really is to be on the human lineage. Now, archaeology is about the things that we make as humans and generally discard. So when is the beginning of archaeology? Well, it's a lot later that we see the first stone tools. Definitively, about 2.6 million years ago in Eastern Africa, we have stone tools called the Older One. Sometime around 2.6 onwards, maybe a little earlier. Recently, there was an older site at about 3.3 million years, but it's highly contested. And ultimately, this time period is a fascinating time period where we're going from those bipedal apes to things that begin to look a little bit more like us, the beginnings of our genus Homo. That's really when archaeology begins. And it's also the beginning of what we call the Quaternary period. This is a period where we get these glacial, interglacial periods, these warm and cold phases of ice age cycling. And this has a huge effect on human evolution. So as a paleoanthropologist, as a geochronologist, we sort of know that we have all of these different species. And in the past, you may have seen these all sort of in a line evolving one to the other. But as time has changed, even over the last 30 years since I was at the university as an undergrad, so many fossils have been found. And we went from what seemed like a more linear timeline to something that looked a little bit more like a tree, and now perhaps a braided river where things are splitting apart from each other, maybe going back together and interbreeding again. But what we now know is that today With us being the only human ancestor in existence, that's an odd time in human evolution. If we look through the past, there's always been multiple species on the landscape. 40,000 years ago, the Neanderthals were still in Europe. 100,000 years ago, the weird hobbit Homo floresiensis was living in Indonesia. Perhaps even Homo erectus was still there at that time. Now, the period that I have been most interested in is the period around 2 million years, where we go from being these bipedal apes to the beginning of our genus, and also then this sort of later time period when we have the origin of modern humans. So how do we work out how old this stuff is? We can look at these skulls and say we think this evolved to that and relates to that by looking at the anatomy of the skulls, but we can also put it on a chronological timeline. So there's a whole host of different dating techniques that we can use. And I'm not going to go into all of these, but generally some ones you might be familiar with are radiometric methods like radiocarbon dating. That dates charcoal. We can use potassium-argon dating or argon-argon dating to date volcanics. We can use uranium series dating to date stalagmites or bones. Paleomagnetism is the one that I use using magnetism, and I'll explain a few of these. So if you're going to an archaeological site, the first thing generally that you will get an idea of is, well, what is the general age of your site? Is it Paleolithic, in other words, hunters and gatherers, prior to sort of 12,000 years ago? Is it Iron Age? Is it Roman? All of these things will determine what type of method that you can use. So radiocarbon dating, which is the one that people think about, is a great method, but it only goes back 50,000 years. So if you want to date things 2 million years ago on the time scale that I'm looking at, you need something different. If you're in the East African Rift Valley, where a lot of early hominid fossils have been found, there's lots of volcanics, and you can use potassium-argon and argon-argon dating. Down in South Africa, we don't have really volcanics, so we have to use other things, and I'll explain more about that later. So we also need to know, what is it that you want to date? What is it you want to know the age of? And how does what you're going to date relate to that? So sometimes in certain methods we can use to directly date the archaeology itself. So pottery can be dated using a method called thermoluminescence that basically dates the point at which quartz has been heated. We can date bone directly, in which case we're dating fossils directly using what's called uranium-thorium, or teeth using electron spin resonance dating. These methods often have a lot of technicalities and so are often not that accurate. They give quite large error ranges. Something like charcoal, now that could be archaeological, because that could be directly dating the archaeology if you're dating a fireplace. But if it's just sat there in the sediments, it may not be related to human activity. It could be from a natural bushfire. So you always have to think about what it is you're dating and how it relates to the archaeology you want to date. If you're dating sediments, using OSL, which dates the burial of quartz, ultimately the last time quartz saw light before it was buried, is the archaeology that's in those sediments, was it deposited at the same time? Or perhaps it's been reworked from somewhere else. You can look at whether the stone tools, for example, have been eroded or not. And all of this information together can help you work out the age of the archaeology you're interested in. So if we go to our archaeological site, well, archaeologists dig holes in the ground. And generally, the first thing that tells us the age of something is what's called the law of superposition. In other words, if it's deep in the ground, at the bottom, it's older, and if it's at the top, it's younger. That generally works pretty well. If you're in caves, lots of weird things can happen in caves, and it's a little bit more complicated, but generally we can do that as archaeologists. So we can look at the archaeology itself if we've got very, very long sequences. So here's an example of a site that I work at a place called Kilombe in central Kenya. There's a very long sequence of deposits. We've got all of these different sections, and we've been able to work out how they go together by looking at the archaeological material in the first place. So right at the bottom, we have this older one technology. So this is the material that first occurs around 2.6 million years ago. And then a little bit further up, we have what's called the Acheulean. These are characterized by what we call large cutting tools or hand axes. These are these sort of iconic things that we find all across the African landscape. Now we know that those first occur about 1.8 million years ago. So it must be younger than that roughly, unless of course we found the oldest of them ever made. They last all the way through though till about 300,000 years ago in some cases. So it doesn't really tie the age range down that much. Around 500,000 years ago, we have what's called the beginnings of the Middle Stone Age. We see smaller stone tools that would have been hafted onto wooden bits of wood. So we get points and blades and a particular way of making stone tools, a prepared way of making stone tools called Lavallois. So we can use this as a very rough outline. Of course, we want it to get it more accurate than that. So we can use certain radiometric dating methods. And I've already said how if you're in Eastern Africa, there's lots of volcanics. And with volcanics, you can use Potassium-Argon or these days argon-argon dating. So I said how radiocarbon dating only goes back 50,000 years. Well, the reason for that is what's called its half-life. Okay, so radiocarbon, carbon-14 decays to nitrogen. Okay, so the carbon is what we call our parent isotope. It's what's there at the beginning. And when it decays by radioactive decay, it turns into nitrogen, which is its daughter product. Now, after 5,730 years, half of the carbon that was there has turned into nitrogen, has gone from the parent to the daughter. And then another half in another 5,730 years. So by 50,000 years ago, there's not really much left to date of the parent material. Now, if we look at something like Potassium-Argon, that has a half-life of 1.3 billion years. So we can use that to date much, much further back in time. Or in South Africa, where we date stalagmites in caves, we use uranium-lead dating. And that has a half-life of 4.5 billion years, essentially the age of the Earth. And that method has been used to date, the age of the Earth. So if we put our argon-argon dates into our Kilombe sequence here, we can begin to see that we can fill things in a little bit more. At the bottom, we now know that the sequence is not older than about 2.493 million years. So sadly, our older one is not the oldest ever found. However, we have a number of other ones around about 1.8 to 1.76, and that's where we get the last of the older one and the Acheulean artifacts. So maybe some of the Acheulean could be some of the earliest that we know. And then the Middle Stone Age is up there after about 469,000 years, sort of where it's meant to be. We're still filling in this sequence, so hopefully things will get better. But that brings in other methods, and particularly the method that I do, which is the reason I went to Kilombe in the first place. So I use a method called paleomagnetism. So this is a method that ultimately looks at how the magnetic field has changed through time. This gets recorded in volcanic sediments when they cool, or in sedimentary deposits in lakes or in caves when the water is flushed in and all the little magnetic grains fall out of suspension and they align themselves with the Earth's magnetic field. Now today, north is where north is, south is where south is, but that's not always been the case. 780,000 years ago, the Earth's field was actually the other way around. North and south had switched themselves. And that happens quite often if we look back through geological time. And we know when all of these reversals occur because people have been studying this since the 1970s. So we can go to our sites and we can sample up through the sections and see, is it pointing north or is it pointing south? We compare that to the globally known record and we can work out an age for our site. Ultimately, and if it's pointing north like it is today, we call that normal. If it's pointing south, we call that a reversed field state. And if it's sort of in the middle where it's actually reversing, which is hard to find, we call it intermediate. So I went to Kilombe, and this is very early in this sort of analysis, and we did some sampling through that area there where we saw the 1.8 million year old argon-argon dates. And we did that because we know that there's a magnetic reversal there at around about 1.78 million years. And in actual fact, we just found the end of it just around about the layer where the older one, the main older one stone tools are. So we're then able to say with certainty, yes, this is around about 1.78 million years. So when we can combine all of these different methods together, generally it gives us more precise ages. And each one reinforces the other one. This is another example of another site in Kenya that I worked at doing a similar sort of thing. They didn't actually argon date the volcanic layer at this site. What they did is they geochemically fingerprinted it. Each volcanic eruption has a specific geochemical print, and we can actually therefore use that to identify which volcanic layer is which volcanic layer. So we knew that the layer at the top was what's called the KBS tuff, which is about 1.869 million years. And again, we know that there's a magnetic reversal at 1.95 million years. So in theory, if we sampled down, we would eventually find that. So that's what we did. And again, we were very lucky because the date that had the archaeology, this is an older one site, was just below the 1.95. So we're able to say that it was around about 1.95 million years old. So that brings us sort of to South Africa. Now, South Africa is more difficult to date sites. Always has been. This is what I started my PhD on. When I started my PhD in the late 90s on this, there were virtually no good dates for any of the sites in South Africa. And that's because there isn't volcanic material. And so we need other methods. So I now work at a site called Drimolen, or this is what's called Drimolen Main Quarry, which is just outside of Johannesburg. So this was most well known for the most complete skull of a species called Paranthropus robustus, DNH7, that was found in 1994. Paranthropus robustus is sort of a little bit like the weird vegetarian side branch of human evolution, an ultra specialist human that was very, very successful for over 1 million years before they went extinct. But it's a really interesting and fascinating species because it also lived alongside some of our first more human ancestors. So this hole in the ground may not look much like a cave anymore. It doesn't, but part of that is it's so old that the sediments which have become solidified, the roof has been eroded off the cave. And then actually in the 20th century, people came in and mined out the stalagmites and the stalactites from the cave. And so there's this big hole there, but all of the fossil-bearing sediments are sort of left adhering to sort of one wall. Some of it sort of collapsed in, which is where DNH7 came from. But we've got this big slice right through the middle of the cave, so we can see all of the stratigraphy. So more recently in our excavations, we found a whole host of new fossil material, new crania. DNH155, which is another Paranthropus, DNH134, which is a early Homo skull, and 152, which is a Paranthropus, and then 153, which is a partial skeleton that we don't really know what it is yet. Hopefully when we go back, we'll be able to find more. So DNH134, Simon, it's named after a collaborator of ours who sadly died, was found by a second year La Trobe University undergraduate student, Richard Curtis, in 2015. When he dug it up, we didn't actually realise it was a hominid. We thought it was a baboon because it was in lots of different pieces and it had a very, very thin crania. But when we began to put them all back together again, the brain got bigger and bigger and bigger. And we sort of realised this is not a baboon. And when we looked at the shape of it, we began to uncover other interesting things about it. But it's a very young individual. It's older, probably slightly older than perhaps 1.5 to 3 years old, which is sort of why we mistook it initially when it was in all its different pieces. And then in 2018, we found this complete skull of Paranthropus robustus, or DNH155. And that was found by a second year field school student from Canada, Samantha Good. The top left there is as she sort of began to find it, the skull was actually upside down. And then we took the whole block out. You can see it in the whole block just there to the left of Samantha. And we took it all out and then we prepped it sort of back at the field camp and excavated it all out and started putting it all back together again. So how do we date Drimolen? Well, Drimolen's made up of a number of different things. What we call breccia. So breccia is basically collapse. It's everything that's come into the entrance of the cave. It's been swept off the landscape. It's bits of the walls, bits of the ceiling. So you've got all of these fossils and fine-grained sediment, but big sort of chunks and clasts as well. So we can use a method called electron spin resonance dating to date the teeth of the actual fossils directly from the breccia. Can't use paleomagnetism because it all collapses so quickly it doesn't really work. There's no volcanics. We can use biostratigraphy, trying to work out the age of something by looking at the different fossils that are in there. But electron spin resonance is sort of what we've mainly used to try and directly date the breccia bit of the site. Now, when it floods, the water flushes through the breccia and it picks up all the little bits of it and it sort of washes it to the side of the cave. And you see all these little flood lenses, coarse, fine, coarse, fine, coarse, fine. And those are little floods. You often find little rat fossils in there as well, which can also be good for dating. So this is the perfect thing for paleomagnetism, stuff that's been swept into water and then sort of fallen out of suspension. So we use paleomagnetism to date this bit, which forms at the same sort of time as the breccia. And then the other thing that we have is what we call speleothem. So speleothem is basically any form of cave mineral. So stalagmites and stalactites, as you would see if you went to a show cave. You can see me here in a show cave in South Africa, just in front of all of those stalagmites. Stalagmites being on the floor, stalactites coming down from the roof. And you can see here, this is a big basal stalagmite layer at Drimolen that we dated using uranium-lead dating. That's the one I said had a 4.5 billion year half-life and can date the age of the Earth. Until recently, it was difficult to date really young stuff, but now we can do it. As long as we can find really high uranium levels in some of the layers. So when we put all of this together, these three different methods, we get this sequence here. So ultimately, all of the fossils are sort of in the lower part of this. So we have a uranium, what we call a uranium series electron spin resonance age, because we do the two methods together on the teeth, of about 2.04 million years. As we track up from that, so that's in a reverse polarity period. So that means that the magnetic field of the Earth is pointing south. But as we go up through the sequence, suddenly it becomes intermediate. It's not pointing north or south. And then if we go further up, it's pointing north again. So we know that we've got a magnetic reversal in there. So we've got another uranium series, another electron spin resonant age of about 1.96 million years, right in that middle bit that's all pointing in different directions. And also there's a little flowstone that formed at that exact same time period. And the flowstone itself records this intermediate direction. And we've been able to date that using uranium-lead dating to, again, about 1.96 million years. So we can therefore be very certain that this reversal is the lower part of the Olduvai. So it's the same one as at that second site in Kenya that I showed you earlier, 1.95 million years old. So we know that the fossils can't be any younger than that, and the electron spin resonance at the bottom at 2.04 million years gives us a good rough age for some of that material. The basal flowstone formed 600,000 years, sort of younger than that, at about 2.67 million years. And you can see here, this is a 3D scan of, well, it's not a 3D scan of the site, it's a 3D model of the site. This is like 6,000 photos that have been stitched together to create this color true sort of 3D model of the site. And basically we can find this reversal all across the site, and so we can use this as sort of marker. And all of our hominids are underneath that, so they're all older than 1.95. So we published this in the journal Science in 2000, and it gave us an age for the fossil material, but also it enabled us to show definitively for the first time that actually there were probably 3 different species living on the landscape at the same time. There was Paranthropus robustus, which we've got lots and lots of fossils of at Drimolen, but also our little sort of Homo skull, not a baboon, which turns out is Homo erectus, is living at the same time. And then around about sort of 6 kilometers away from Drimolen is another site called Malapa, where there's a species called Australopithecus sediba, which is one of the last specimens of this more ape-like Australopithecus fossil. The first one of which was found by an Australian from Queensland, actually, in 1924. So we've got all of these different species living on this landscape at the same time. How they're living on the landscape at the same time, we don't know that yet. That's something for the future. The other fossil, the one that Samantha Good found in 2018, is the most complete male Paranthropus robustus cranium ever found. And in actual fact, when we compared it to DNH7, which is the female fossil that was found back in 1994, they're very similar to each other. But interestingly, quite different from Paranthropus fossils from another site called Swartkrans that's about 6 kilometers away. And part of the reason we think that is because they're of different ages. And what we're actually seeing is microevolutionary change within this Paranthropus species. So we can actually see evolution sort of happening in this lineage. And this is something else that sort of we're exploring. And my PhD students, Jesse Martin and Angie Leese, who reconstructed the skull, led the paper that we published on this in Nature, Ecology and Evolution in late 2020. Now, the other thing is that not only is our little baby Homo one of the most sort of complete cranial vaults that we've got of that genus in South Africa, because they normally get crushed. We've got lots of other ones that have sort of been crushed by rockfall. But as it turns out, it's Homo erectus. And actually, it turns out it's the oldest Homo erectus anywhere in the world. So prior to this, there was a whole series of fossils from Dmanisi in Georgia that were about 1.8 million years old. And there's some other bits and pieces in Eastern Africa that is, perhaps 1.9 million years old. The more complete sort of skulls from Eastern Africa are only around about 1.6 million years. So this perhaps seems to be the beginning of Homo erectus. And Homo erectus is this sort of iconic species that really represents the first time we've got something definitively more human. It's got a bigger brain, a bigger body size. And also it's the first hominid to leave Africa and spread all over the world. It's the first global traveler. So this is pretty cool. So ultimately, if you were interested in any more of this, if you're studying archaeology, or even if you're not, and you wanted to come on a field school to South Africa and see if you can find your own early hominid to dig up, then we do run the Drimolen Field School in June every year. We haven't done for a few years because of COVID, but June 2023, we're hoping to get back there and begin excavating again. And I also excavate at Amanzi Springs, which is in the Schulian to Middle Stone Age site, in November each year, and we'll be going there in 2022. Other things, so I run at La Trobe, I run the first year intro undergraduate subject Arc 1 THJ, or the human journey, which basically looks at the 7 million years of human evolution. And we have this massive skull cast collection and skeletal collection of all of these different hominid species that help us understand who we are and where we came from. You can do that as part of our archaeology degree, as a BA major in archaeology online, or soon in open as part of Open Universities Australia. So I hope that's interested you, and I hope to see you at La Trobe soon.